So Betelgeuse was initially as a very massive star fusing hydrogen into helium. Then it left the main sequence, ascended the red, and then the red supergiant branches.
It ran out of hydrogen in its core.
Ran out of hydrogen, needed to do something else.
For years, astronomers have been watching one star more carefully than almost any other. Not because it's the brightest, not because it's the closest, but because it's unstable. Betelgeuse, a red supergiant sitting in the shoulder of Orion, roughly 642 light-years from Earth. Massive, aging, violent. A star that has already entered the final phase of its life. Scientists have known for decades that Betelgeuse will eventually explode. The only question has always been, when? But what the James Webb Space Telescope is now observing isn't just instability, it's escalation. And that escalation doesn't look exactly like the models predicted. Betelgeuse is enormous, roughly 700 times the radius of our Sun. If it replaced our Sun, its outer atmosphere would extend past the orbit of Mars. But size isn't what makes it dangerous. Instability is. Red supergiants like Betelgeuse are powered by layered nuclear fusion deep in their cores. As they near the end of their lives, those fusion layers become chaotic. The star swells, contracts, erupts, sheds mass, pulses unpredictably. In 2019, Betelgeuse dimmed dramatically, an event now known as the Great Dimming. For months, its brightness dropped to levels never recorded before. Speculation exploded across the globe. Was this the beginning? Was it about to go supernova? The answer turned out to be more complex. A massive surface ejection combined with dust formation temporarily obscured the star. But that event changed something important. It proved Betelgeuse was capable of violent structural shifts on short timescales. Now fast forward. The James Webb Space Telescope has been monitoring Betelgeuse in infrared, a spectrum capable of penetrating dust and revealing deeper thermal structure. And what Webb is seeing now suggests something has changed again. When astronomers compared earlier infrared scans with the newest data, they weren't looking for spectacle. They were looking for trend. And the trend shows growth. Not metaphorical growth, physical expansion of instability regions. Surface convection cells, enormous boiling plasma structures, are covering more surface area than previous models anticipated at this stage. Some of these cells are so large they dwarf Jupiter. That isn't unusual by itself, but the footprint of the unstable regions has increased. Infrared emission intensity from certain hemispheres has strengthened. Localized mass ejections are extending farther outward, and the shift isn't evenly distributed. One side of Betelgeuse appears to be destabilizing faster than the other. That asymmetry is what's seriously off. Massive stars nearing core collapse are often modeled as roughly spherical in their instability, but Webb's data suggests distortion. Magnetic field irregularities are becoming more pronounced in certain zones. Plasma plumes are stretching in directional arcs rather than symmetrical halos. Density gradients beneath the photosphere, the visible surface, appear uneven. This doesn't mean Betelgeuse is exploding right now. There is no confirmed supernova, but it does suggest the internal structure may be reorganizing in ways not fully accounted for in classical stellar evolution simulations. Here's why that matters. When a massive star collapses, its core implodes in milliseconds. The outer layers rebound outward in a supernova explosion. In idealized models, that process begins from a relatively centered collapse. But if the core becomes unstable unevenly, if pressure distribution fractures instead of compressing uniformly, the explosion can become asymmetrical. Asymmetrical supernovas behave differently. They eject matter unevenly. They produce neutron stars that can kick at extreme velocities. They generate gravitational wave patterns that deviate from spherical collapse signatures. Webb's observations show shock signatures propagating through the outer envelope of Betelgeuse, but those shock fronts are not expanding at identical rates in all directions. Some are accelerating faster. Some appear dampened. That suggests layered turbulence rather than smooth decay. There's another development. Webb's infrared instruments have detected increasing dust formation in regions previously stable. Dust formation is common in red supergiants, but rapid dust production can indicate intensified surface disruption. And intensified disruption suggests deeper structural instability. What's especially interesting is how these changes compare over time. Earlier scans showed confined convection. The latest scans show expanded convection zones. Earlier scans showed localized mass ejection. The latest scans show broader displacement fields. The unstable region has grown. That growth is measurable. Not dramatic, not cinematic, but measurable. And measurable change is what astrophysicists care about most. Because stars don't explode randomly. They reach thresholds. Fusion stops supporting the core. Iron builds up. Gravity wins. But the path to that threshold can vary. Betelgeuse's current behavior suggests it may not follow the clean, symmetrical pathway often presented in textbooks. Instead, it may destabilize in stages, fragmented stages. Some researchers are examining whether what Webb is seeing represents pre-collapse turbulence, a final rearrangement of internal energy layers before catastrophic failure. Others caution that red supergiants are notoriously unpredictable and can experience multi-year instability cycles before returning to temporary equilibrium. That uncertainty is part of what makes this moment significant. For the first time, we're observing high-resolution, time-layered instability patterns in a nearby red supergiant. Previous supernova studies have mostly been post-event analysis. We see the explosion, then we reconstruct what likely happened. But Betelgeuse offers something different, a live instability timeline. And that timeline is showing escalation. Convective cell enlargement, magnetic torsion increase, infrared intensity amplification in localized zones, surface mass displacement spreading outward. If collapse were to occur, it would not be sudden from our perspective. The light would take 642 years to reach us. In reality, the event could have already happened, or be centuries away. But what matters is the instability profile, and that profile appears to be intensifying. Now let's address safety. Even if Betelgeuse exploded tomorrow, Earth would not be in danger. At 642 light-years away, it is far outside the lethal radiation zone. The supernova would likely appear extremely bright in our sky, potentially visible during daylight, but it would not strip our atmosphere or sterilize the planet. The concern is scientific, not existential. Because if Betelgeuse collapses asymmetrically, it may provide the first detailed dataset linking visible supernova evolution with gravitational wave signatures. It may reveal whether massive red supergiants transition directly into neutron stars or if fallback mechanisms temporarily resist full collapse. It may refine our understanding of how heavy elements are distributed into the interstellar medium. Webb's spectral analysis is already detecting shifts in elemental distribution within the ejected material. Carbon and oxygen signatures are expected, but the ratios are evolving. That suggests mixing layers inside the star may be reconfiguring, and that reconfiguration may indicate internal pressure imbalance. Which brings us back to the core issue. The instability region is growing. The turbulence is spreading, the asymmetry is increasing, and it's happening in a star already known to be nearing the end of its life. Betelgeuse is not stable. It hasn't been for decades, but the rate of change appears to be accelerating, not smoothly, in bursts, in spikes, in expanding thermal zones. That doesn't guarantee imminent collapse, but it does suggest that the internal equilibrium is shifting, and shifting equilibrium in a red supergiant is never permanent. Eventually, gravity wins. Whether that happens in our lifetime or centuries from now remains unknown. But Webb has given us something unprecedented, a close-up view of stellar instability as it evolves. And what we're seeing isn't neat, it isn't symmetrical, it isn't perfectly aligned with theoretical simplicity. It's messy, layered, expanding. Something is changing, something is intensifying. And in astrophysics, intensification late in stellar evolution rarely reverses indefinitely. Betelgeuse will explode one day. That's not speculation, that's physics. The only unknown is timing. But if the unstable regions continue expanding, if the asymmetry continues increasing, if the internal turbulence continues escalating, then we may be closer to that threshold than we once thought. Not because of drama, not because of headlines, but because the data shows measurable growth. And when instability grows inside a star this massive, it doesn't shrink quietly. James Webb is still watching, the data is still coming in, and Betelgeuse is still there, glowing, shifting, destabilizing. The real question isn't whether it will explode, it's whether this growing instability is the beginning of its final phase, or just another violent chapter in a long, chaotic decline. Either way, we're watching something rare, a massive star under stress, and the stress is increasing, and that is what's seriously off.